Thank you for joining our e-seminar, The Need for Speed, Enhancing Lab Productivity and Sample Throughput with ICP-OES and ICP-MS. My name is Aaron Heineman, the Inorganic Product Line Leader for PerkinElmer, and with my co-presenter, Ruth Merrifield, we'll guide you through some thoughts to help you in your journey in enhancing your laboratory's productivity. Normally, we would discuss analytical challenges such as accuracy, precision, calibration range, analytical range, long-term stability, spectral interferences, matrix interferences, or potential ionization interferences. And all of those are important challenges to understand and to have a plan to avoid. There will also be some laboratory challenges that we need to review. So laboratory challenges such as sample preparation, quality control, how to deal with rush samples, standards and standard preparation, also time, the time to get the samples run and the results reported to your customer. Remember, when developing or optimizing a method to mitigate these challenges and enhance productivity, you need to know your samples and, just as importantly, know what your analytical objectives are. The chart on the left shows how different applications fall into the analyte versus matrix graph. Environmental is a broad category, and samples such as drinking water can have low matrix and analyte concentrations, or there can be high matrix in soils, wastewaters. Analytical objectives could be understanding what analytes you're looking for, your matrix tolerance, your quality objectives, and detection limit requirements. Next, to help mitigate challenges, know your instrument. Know, is the system ready to go? Is it ready to do the work? How do you know? What is my setup? Do I have the right sample introduction system? And what is the condition of the sample introduction system? Make sure you log things. It helps you to know your instrument and the condition it's in. Now, really, the tools to help meet challenges is the instrumentation the analyst has. So the instrument provides tools to help with the various challenges that the analyst meets. Resolution minimizes spectral interferences, and it may allow for the use of a more sensitive wavelength. In ICP-MS, resolution and abundance sensitivity help mitigate spectral overlap as well. Stability is important for long-term precision and to minimize drift. The transport efficiency of the sample introduction and optical throughput is important for detection limits as well as precision. The detector is an important consideration to understand the instrument's dynamic range and the possible detection limits. Universal data acquisition and total quant functions allow for sample screening for ICP-OES and ICP-MS respectively. So some additional tools that can help the analysts meet their challenges in the instrumentation. For ICP-OES, we have full range dual view, no maintenance axial view with plasma shear technology in the Avio system, helps eliminate easily ionizable element effects, and extends the analytical range of the instrument. In ICP-MS, the NexION series ICP-MS, we have universal cell technology, which provides us with the ability to reduce interferences, avoid spectral interferences on our analytes of interest. It also allows us to extend our dynamic range, allowing us to calibrate to a higher concentration. Also, software. It's another tool for the instrument to meet our challenge. Last but not least, automation. Automating the system, we're using an autosampler and high-throughput systems, allow the analyst to meet the productivity demands of their laboratory. Well, today's focus is time. Time is a challenge for us all. In analytical chemistry, we want to use the tools to speed up our method. We want to increase instrument uptime reduce downtime and reduce maintenance of the systems. We want to reduce reruns. We want to have a less carryover in the system, and so we can run more samples in less time. So to that end, PerkinElmer has recently released the new S20 series of autosamplers with an increased capacity compared to the previous PerkinElmer generation. The S20 series offers capacity up to 270 samples for the S23 model and up to 450 samples for the S25, allowing for longer unattended runs. The S20 series features speed enhancements with movements up to 330 millimeters per second and integration with all of PerkinElmer's spectroscopy software. In addition, PerkinElmer introduced the High-Throughput System, or HTS. The HTS system consists of a metal-free 7-port valve, 4-channel peristaltic pump, and a high-speed vacuum pump that expedites the sample loading and washout process. The HTS is another tool in your analytical toolbox for better productivity, performance, and value. We've designed this modular system to be rugged and stable, providing the laboratory increased productivity, resulting in more samples in less time with less maintenance. These productivity and performance improvements allow you to get your results out faster, providing greater instrument value. The value of the PerkinElmer HTS is improved by having integrated control in Syngistics for ICP-MS as well as Syngistics for ICP on the NexION and Avio respectively. This improvement in user experience results in ease of use, setup, and cross-training benefits for the instrument operators. To establish and ensure a rugged and stable design, the HTS has been tested with a variety of matrices. 3 strong acid matrices are listed here. In addition, countless hours of repeated injections were performed during the development to ensure reliable operation. Ultimately, with flow injection using the HTS method, throughput can be dramatically improved, with significantly less sample reaching the sample introduction system and the cones on the NexION ICP-MS. The next logical step is the combination of this automation to provide a complete offering. These complete productivity offerings can accommodate low to mid sample volume laboratories with the S23 and mid to high sample volume laboratories with the S25, with PerkinElmer providing the full service and support of this complete solution will help drive greater return on investment for the laboratory. So, one final consideration when enhancing your laboratory's productivity is the integration times of your methods. I hear or see integration settings in many analytical methods that are way too long for the application's requirements. A common myth is that longer integration times results in better data. The truth is that there is a point where a longer integration will only increase your overall analytical time and not provide better detection limits, as many elements, especially for ICP-MS, are background limited. The Avio 500, an auto integration between 1 and 5 seconds, is adequate for most applications. The NexION, we typically aim for about 500 milliseconds per replicate. Remember, all we need to do is meet our analytical objectives so that the method is fit for purpose. So, in conclusion, know your samples, know your instrument, use the technology, and then design your analysis around your samples. If the hole is round, use the round peg. Then optimize your method. Don't spend time where there is no payback, particularly integration time. Now I'll hand it over to Ruth to review some data that was collected using the latest in automation from PerkinElmer.
Thanks, Aaron. Today I will talk about the High-Throughput System, or HTS, and S20 series autosamplers, and show some results on their integration on both our Avio and NexION platforms. The same wastewater, soil and sediment CRM samples were run on both systems. Let's start by looking at the results on the Avio 500. The Avio 500 ICP-OES was paired with the HTS and S23 Autosampler. The Avio 500 is a simultaneous ICP-OES. It has the capability to run in both axial and radial modes, or a combination of both. The Avio 500 captures spectra on both the UV and visible detectors simultaneously, meaning that it can reduce the speed of analysis. Another unique feature of the Avio is its universal data acquisition, which allows for the instrument to capture the entire spectra with no time penalty, allowing for post-analysis reprocessing of either different elements, providing they were in the calibration standard, or different wavelengths if an interference is suspected on a specific sample. In this case, the Avio 500 was also run in conjunction with the PerkinElmer High-Throughput System and S23 Autosampler. The High-Throughput System, or HTS system, allows for rapid uptake and delivery of the sample to the instrument by using a vacuum-filled loop and injection valve. It also reduces carryover by cleaning the probe and probe lines using the vacuum system during analysis time, and then rinses the remaining sample from the loop, also using the vacuum system. In the top right-hand corner, you can see some of the Avio 500 parameters. As you can see, a variation on the timings of the EPA 200.7 method were used, with 3 replicates and an acquisition time of between 0.5 and 10 seconds. The HTS timings can be seen in the top right-hand table, where the total time for sample uptake and rinse being 18 seconds. The average read time was 1 minute and 30 seconds, meaning the average sample-to-sample analysis was 1 minute and 48 seconds. The sample dilution factors for the CRM materials can be seen in the table at the bottom right. All samples were diluted with ultra-high purity water and acidified to 2% nitric acid. All the standards, the carrier solution and the internal standard solution were all acidified to 2% nitric acid as well. The internal standard was added within the valve and was at an initial concentration of 20 ppm yttrium. The internal standard recovery was stable throughout the run, as you can see in the graph on this slide, with less than 10% change throughout the entire analysis. A continuous calibration verification, or CCV, was measured every 10 samples throughout the analysis. You can see from this slide that we get good recovery of the CCV throughout the experiment, and it is within plus or minus 10% of the expected value. The table on this slide shows the elements measured and the wavelengths used. These were based on the EPA method 200.7. The detection limit was calculated from the standard deviation of 10 consecutive blank measurements, and show that all measurements were within the low ppb or high ppt range. An initial calibration verification was also made. This was done with a second source, and you can see the expected values along with the measured values and the recovery on the right-hand side of the table. You can see that the recovery was between plus or minus 5%. Different types of water samples were run to show the recovery on various different CRM materials. This was used to show the robustness of the system, with washout between samples containing high and low concentrations being consistent throughout the analysis. On this slide, we show the first sample, which is a wastewater CRM material. The table shows the expected value in ppm, the average value of all samples run throughout the 6.5-hour time period, of which there were 20. The RSD of these values shows there is not much variance throughout the analysis. This can also be shown on the graph on the right-hand side, where the average recovery for all samples is stable throughout the analysis time. The average recovery can also be seen in the table, where the elements are within plus or minus 10% of the expected value. The second sample was another wastewater certified reference material. Again, you can see a good average recovery of the 20 samples with low RSD values observed. Showing good consistency of the HTS sample introduction system. The third example is a soil sample. This sample has a wider variation of elemental concentrations than the previous two samples. It also contains some elements where the concentrations were much lower than in the previous samples, showing there was no carryover observed. Once again, you can see good correlation on the average sample recovery with the overall stability of the measurements shown in the graph. The final sample is a CRM river sediment sample. Once again showing good stability over measurements over time, and a large variation of elemental concentrations. The back-to-back analysis of these different sample types and matrices showed the excellent stability of the HTS system both on sample uptake and elemental washout. Next, we will talk about the high-throughput system on the ICP-MS. In this case, we ran the same samples, but on our newly released NexION 5000. The NexION 5000 ICP-MS was again paired with the HTS introduction system and S23 autosampler. The NexION 5000 is a multi-quadrupole ICP-MS with triple quadrupole capabilities, along with both KD and DRC interference correction using a universal cell for both collision and reaction modes. It allows for the selection of an ion mass before and after the universal cell. This technology can be particularly effective when analyzing elements that have large backgrounds or interferences. When analyzing waters and soils, elements such as arsenic, selenium, and phosphor are necessary to measure, and in some places the required detection limits by governing bodies and agencies is being lowered. These elements have interferences that are produced in the plasma, such as argon chloride on arsenic, argon-argon dimer on selenium, and nitrogen oxide on phosphor. These interferences can be high in concentration and difficult to remove. However, all of these elements form oxides easily and can be mass shifted using the NexION 5000. On this slide, we will use arsenic as an example, where arsenic is interfered with by argon chloride, as they have the same mass. These will both then pass through the Q1 filtering system at the front of the ICP-MS. All other elements will be rejected. They then enter the reaction cell, where the arsenic is reacted with oxygen to form arsenic oxide, while the argon chloride is not affected. The arsenic oxide is now at a higher mass and is passed through the second quadrupole, while the argon chloride is rejected. The arsenic oxide is now free from any background and the detection limit is lowered considerably. In the following example, we will use both KD and oxygen modes, or helium and oxygen modes, to be able to remove interferences as well as keeping speed of the instrument. On this slide, we can see the parameters for the NexION 5000, along with our sample preparation, where we've had a higher dilution factor than we did for the Avio samples, and our HTS parameters and timing. In this case, the HTS took 12 seconds for a total sample uptake time, and 12 seconds as a total wash and autosampler move time, giving a total HTS time of 24 seconds. The sample analysis time was 2 minutes and 43 seconds, giving a sample time of 3 minutes and 7 seconds. The NexION 5000 can be used with multiple different gas modes and ion guide modes, or IGMs. The IGM mode relates to which mass is being filtered on the first and third quadrupole, as well as incorporating which gas is being used for analysis. The more gases that are used during analysis, the more time that will be required for each sample. However, different gases will ensure lower detection limits and superior interference removal. For this example, we wanted to go for the speed of analysis, and so we kept the gas modes to just 2. In this case, helium for collision mode and oxygen as a DRC reaction mode. The multi-quadrupole technology of the NexION 5000 allows for the mass shift to be used in the case of elements such as arsenic, selenium, and phosphor, as was previously discussed. On this slide, you can see the IGM and gas modes for each element analyzed. The Q1 refers to the mass filtered on the first quadrupole, and Q3, the mass filtered on the third quadrupole. The gas mode can be seen here. Any element, such as selenium oxide, where the first mass and the second mass are different, will be used in mass shift mode. However, there are some elements that we just used oxygen to remove the interference, such as cadmium 111. The detection limits for all 30 elements can also be seen on this slide. An initial calibration verification was taken after the calibration from a second source to verify the calibration. You can see that all elements came back within plus or minus 10% of the expected value. A continuous calibration verification, or CCV, was also run every 10 samples throughout the analysis. As you can see, all elements were within plus or minus 10% of the expected values throughout the entire experimental analysis. The HTS affords superior washout between samples, thus reducing analysis time. Here we will compare the washout time between a system using an HTS and one without. Both systems used the S23 Autosampler. We used the standard method, which incorporated a wide range of elemental masses. The system was calibrated for each element. A high standard was then analyzed, followed by 10 blank samples, to assess the washout time for the system with and without an HTS. Here we will only show the data up until the point a washout was completed. Adequate washout was assumed when a blank was below 0.2% of the sample that was analyzed, or there had been a 99.8% washout of the system. In the top table, you can see the results without the HTS system, where the rinse was performed using the standard Perry pump. The analysis of the sample showed that there was a good recovery of the expected value. Here you can see the target concentration of the sample and the percent recovery. However, when it came to rinse, all elements failed within the first rinse cycle. Most elements passed on the second rinse cycle, taking an average time of 176 seconds, sample to adequately rinse those elements. However, mercury, which is known to be sticky, took a lot longer to rinse out of the tubing, taking an average of 440 seconds sample to sample. Comparing this to the analysis using an HTS system in the bottom table on this slide, where the loop rinse time had been set to 8 seconds, you can see that again all elements reached within 1% of their target value for the analysis. However, this time all elements adequately rinsed out to over 99.8% rinse out over the first try. This gave an average sample to sample time of 94 seconds, essentially doubling productivity. The same 4 certified reference materials were analysed over the same time period on the NexION 5000 as they were for the Avio 500. This time, the samples were analysed 9 times overall. So each mean or averaged recovery and RSDs are over 9 measurements. Again, we show that there's a good correlation between the expected value, the average measured value, and the percent recovery. The RSD values are all low, showing stability of the analysis with time, which corresponds to the graphic on the right-hand side. The second wastewater certified reference material also shows a good correlation between the expected value and the average measured value and recovery, also showing low RSDs, and the stability of the system can be seen on the graphic on the right-hand side. The soil certified reference material shows the ability of the system to measure a range of concentrations, with some elements such as cadmium, cobalt, and antimony being measured at levels over 100 times lower than in the previous sample, thus exhibiting no carryover, as well as showing good recoveries and RSDs throughout the entire analysis. Finally, the river sediment sample was measured, showing the same stability in the analysis throughout with no carryover observed from the previous sample. In conclusion, the High-Throughput System, or HTS, and S20 series Autosamplers integrate seamlessly with both the Avio and NexION platforms. Both sample uptake and washout times are greatly reduced using the HTS system, especially for difficult elements such as mercury. 4 CRM materials were analysed on both the NexION and Avio systems. These materials showed a wide range in elemental concentrations, and recoveries were consistent on both instruments. No carryover was observed between samples containing high concentrations and low concentrations. That concludes my section of this presentation. Now I will hand back to Erin for the Q&A session.
Thank you, Ruth. We're now going to begin answering the questions submitted during today's presentation.